share my screen. If you can make me host.
Yes, I think you can now share your screen. Do you see that? Do you have the option?
Yes, I do. So can you see the screen?
Yes.
Okay, so I just make full screen. The speaker, yeah. So I also start with presenting myself a bit broadly. I am from Turkey and I made my bachelor degree in Turkey and the lecture part of the master degree in Turkey and the thesis I have done in Padova University in the physics department. And I graduated from Turkey in Çukurova University in Adana. And then I got a Erasmus Mundus fellowship and I moved to the Europe. And so first year I was in Naples, in Italy, working on supernova. And then the second, third year I was in Nice in France, working on gamma ray burst. And so then after that, I moved to Sweden for postdocs for 3 years. I work with Felix Wright, who is the collaborator of the as a pair. And then I moved to Germany for 2 years postdocs. I was guest postdoc there. I continue my work with Felix Wright, and we write several papers in the last 2 years. And this presentation will be mostly concentrated on that papers. So the title of my talk is the classification of the photospheric emission in the short GRBs. These are the papers. I will come after this because it also motivated my last paper. So first I will give an introduction to the gamma ray burst. And then after I will talk about the motivation about the papers. It will be more, this part will be a bit larger because what I done also in my last paper is similar things. And then the results will come. Lastly, I will conclude and give the discussion that results come from these results. So the gamma ray burst discovered by Vela satellites in 1967. And they are found that they are isotropically distributed in the sky by the BETSET results, as you can see here. And they also confirm
don't see
that...
the shell, or
Sorry?
at least I don't see the shell.
You don't see the sharing the screen?
Not me, at least.
What do you see?
I see Husne.
Okay.
I see.
Okay.
I see.
Now
okay.
I found it. It's okay. It's
okay.
working strange on the phone. I don't know.
Okay, then it's good.
Okay, so.
Yeah, so this is the first introduction part. So they made a map of the gamma ray burst, and they found that they are isotropically distributed on the sky, and they also confirmed that they are in the cosmological distance. They are external sources, not galactic sources, and this is confirmed with the photospheric. Spectroscopic and the photometric estimation of the gamma ray burst redshift. And then they release an enormous amount of energy. It is in the order of 10 to 54 ergs. So we identify, sorry.
Husne, I'm sorry for interrupting, but is it possible to full screen the presentation?
I tried actually.
I see.
Maybe wait.
On the bottom, there's on the bottom row, you have like 4 squares in the screen to the right of it. Go down.
No, it's on the bottom.
Yeah.
Here?
Yes.
Oh, okay.
A little to the left.
Yes. Yes, exactly.
That one.
Okay, perfect. Yeah, thank you. Sorry.
Thanks.
So I also close maybe this. So then we identify gamma ray bursts from their prompt emission. So the prompt phase has a high flux of gamma ray photons. In this prompt emission, they have a light curve shapes, and these light curves show different behaviors. The number of peak can change, like here, and it can be one peak, like here, or it can be two peaks, or it can be several peaks. And they can have also variability, that the variability can be quite smooth, like like this one, or like this one, or it can be very spiky, like very in each here. This is the best example. So there is it is difficult to differentiate them, but there are ways to differentiate them, that we use this temporal evolution to differentiate the emission, like thermal and non-thermal components, prompt and afterglow emission. And also the people are searching in this days the high energy part of the spectrum. So I will come all these things what they are, but I just wanted to show here. So I want to say that there are.
I have a question.
Yes.
I have a question.
Do you have?
What is the reason for the peaks? Why is it not steady?
Could you repeat it again?
What is the reason of the peaks? Why the gamma ray burst is not steady?
So these peaks, like I will explain how the emission is evolving. So these are like it can be the clue of the different emission mechanisms. I mean, these are the light curve. So they emit photons, and they produce such a behavior. So then why it is different? So this is under this, if it is thermal emission, non-thermal emission. If it is thermal, how is the cooling of the materials? So this is under the emission mechanism, which is not understand very well. Yeah, I hope it's clear. And in the following of the presentation, you will also get more idea about that.
Also, I have a question, small one.
Yes, yes.
The last plot, is there any periodicity, or it's just something else?
In gamma ray burst, the periodic behavior didn't seen actually, but yeah, somehow maybe the same emission mechanism is appearing, but then something is happening, but I cannot say what is exactly for that source. This is like most known properties that they are differentiating the light curve of the gamma ray burst.
Okay, thanks.
But normally there is no periodicity in gamma ray burst. Reputation, let's say. So they have classification, broad classification. That is that they have two distinct classes, and this is here I can show. This is the T90. T90 is the time at which the 90% of energy released from the source. And they made the distribution of T90, and they said, okay, the short GR-BIS, short gamma ray burst, has T90 smaller than 2 seconds, and the long GR-B has T90 larger than 2 seconds. And then this classification also seen in the hardness ratio. The hardness ratio is the ratio between the flux at high energy to the flux at low energy ratio. So they saw that the short GR-B has a harder spectra, and the long GR-B has a softer spectra. And can be also differentiated in their host galaxies, because short GRB originated from the old stellar population and the long GRB is originated from the young stellar population. And they have also different progenitors. Let's say different progenitor scenarios. As you know, the short GRBs can result from the compact binary mergers. This can be binary black hole mergers, neutron star mergers, neutron star black hole mergers. And the long GRBs originated from a cataclysmic collapse of a very massive stars. And so in this collapsar scenario, they both go to the same collapsar scenario. In the center, there's a black hole. It's collimated, it's released a jet, and this is collimated by the matter of the star. And this jet can be also associated with the supernova, because they see the bump of the supernova at the end of the light curve of the gamma ray burst. So in this jet,
can you just in the previous slide about the short gamma ray bursts? You said mergers of a compact binary, and you mentioned black holes. So do you expect from a black hole merger to see a gamma ray burst, to see all these electromagnetic and matter effects when it's two black holes?
Yes, I mean, they are also considering like neutron star black hole, and black hole mergers is for the origin of short chains.
I have the same question as Ofex. I just don't understand the mechanism of how only gravitational situation of two black holes can produce electromagnetic waves, or GRBs, namely.
Okay. On this point, I don't think I can assess to that point.
Okay.
Yeah, maybe Ofek knows better than me.
No, I mean, what I know is just different than what you said. What I know is, at least on the LEGO side, we typically take neutron star mergers or neutron star black hole mergers as possible sources for follow-up electromagnetic radiation, because there's all this matter that's being crashed together, flowing out, magnetic fields, all that electromagnetic mess. For a black hole merger, I expect it to be just, space-time wise, it's just vacuum meeting vacuum. So there's nothing, there's no matter to produce, there's no charges, there's no matter, nothing to actually create electromagnetic radiation. It would have, one could talk about maybe pair production or some quantum effect that happened there, but I don't think that's a major or expected source for GRBs. The neutron star mergers, those I understand, but for black holes, we typically take them. We don't expect to see anything from them, as far as I know.
Okay, yeah. I will let with his explanation, actually. On that point, I will not go.
Okay.
So then this jet is so this the collapsar scenario, these parts create a matter of the shells, and this in the early times there is a dissipation, and this results photospheric radiation. And then when the faster shell encounter the slower one, then it creates an internal shock, which is the prompt identification of the gamma ray burst. And then after, when the shell interact with the medium, this can be interstellar medium or the wind medium, it creates afterglow. And here the afterglow emission observed in several wavelengths. That's why this afterglow emission studied broadly compared to the prompt emission. And this all emission mechanism happen in a different radius, like as you can see here, 10 to 11 centimeter for photospheric radiation, 10 to 13 centimeter for internal shock and 10 to 16 centimeter for the external shock. So in the prompt emission models, there are two emission. The photospheric emission scenario, there are two emission. Prompt emission explained with two emission. The one is the photospheric radiation. This can be thermal. The second one can be the synchrotron radiation. It is a non-thermal. So I just want to remind what is thermal and the non-thermal. Thermal emission is the natural emission of the photons due to the thermal motion of the charges in the material. Synchrotron emission is the generated by the charged particle spiraling around the magnetic fields at the relativistic speeds. So the thermal emission is depend on the temperature of the emitting surface. Non-thermal emission depends on the other things like such as the relative motion of the excited state of the atoms and the magnetic field strength. Since I will discuss more these emission mechanisms, I wanted to define them. So the synchrotron model generally happen in the larger radius. Here's the radius of the jet. So it has some advantages to explain the gamma ray burst. It has two ingredients, magnetic field and the accelerated particles. They are naturally obtained from the shock waves and the magnetic reconnection. The spectrum is broad and it is non-thermal. So it explains very well the afterglow here, this afterglow, and also the other sources in astronomy's field, like active galactic nucleus. And it is very efficient method to extract the energy from the accelerated particles. However, it has some drawbacks. So efficiency to accelerate the particle is low. It's like in the order of it is 2 to 3% of the energy efficiency. However, it is expected that it should be something like around 10% of the energy. Then this is too broad to explain the narrow spectrum that is seen also the gamma ray burst. Like here, it is the width of the light curves that I showed for each GRB, and this is the distribution of that distribution of the width obtained from the each GRBs. And here you can see the black body, which is the very narrow spectrum for the thermal emission. Here is the synchrotron, should be expected, the slow cooling synchrotron, and here is the fast cooling synchrotron. And as you can see, this large part of amount cannot be explained with the synchrotron emission. And another drawbacks is the low energy index incompatibility. So here, as you can see, there is a spectrum which is called bounce spectrum. It has two parameters. One is the low energy spectral index, and the other one is the high energy. Here you can see the distribution of the low energy spectral index here for different sample that they made it. And here is the red line, is the line of the dead, which is -2 or 3, is defined for the synchrotron, that it cannot produce any spectrum above this line. So it can just produce the softer part, not the harder part.
I'm sorry to take you back again.
Yes.
I'm not sure everyone knows what a spectral index is, and since I watch gravitational waves and I don't observe electromagnetic stuff, I'm not sure I know what a spectral index or spectral width means.
So let's say here I just show it. Here, like you can, this is distribution, but let's say that this is the new F-nu spectrum, and here is the energy, and you have this fits the spectra. It is showed like this. It's similar shape, but I'm just showing here. And then there is a low energy spectral index, and then the high energy spectral index, because the energy is increasing from here to here. And then so you obtain the low energy spectra before the peak energy, and then there is the high energy spectral index after the peak energy. So this is
what does the line that says black body mean? Is that all the energy that comes from the temperature part?
Yes, exactly. Yeah. So the black body emission mostly like for the thermal emission. So it is the thermal emission that we say, it is explained by the black body. So it's very narrow. However, the band function has a, it is the representation of the synchrotron emission. Maybe here, yeah, here better. Here is the spectrum of the black body. Here is the spectrum of the band function. Maybe this is, yeah, nu F nu and the energy. Is that clear or?
Okay, so this is the plot I understand.
Yes, so it is the spectra of this is the model, black body model for the spectra, and here is the band function model.
So the band function that goes about 100 times more energetic particles than the black body thermal part. It goes to 10 to the 4. Oh wait, is that 10 to the 5? It's almost 1,000 times more energetic than the black body.
Yeah, I mean, normally it goes, yes, it is. It shows more energetic if the telescope can observe. So as you can see, this part, it doesn't have enough data, so then you cannot define it. That is the problem of the band function. That's why people are trying to introduce other models. But yes, indeed, it can measure the very high energy if the telescope observes. Yeah.
Okay.
I have a question too.
Yes.
Yeah, so 2 slides previously, there was the 2 shocks, the inner shock and the outer shock, and yeah, so the internal shock. Yeah. So you said that happens when the jet meets shells, but
so it is like this jet consists of shells of the matter. So then some shells move faster than the other one. So here in this stage, when the faster shell encounter like collapse or reach to the slower one, then it creates like internal shock. Yeah. Is it clear?
Yeah.
Yes? I don't hear you very well.
Yeah.
Okay. So, so this was the drawbacks of the synchrotron model. And here is the photospheric emission model, because as I said, here the black body, and okay, here is the synchrotron, and okay, but there are some things that cannot be explained with these 2 models. So what people proposed other models. The one of them is the photospheric model proposed by, studied by Asaf Pear and Felix Reide also. So advantages of this model is that it can be very efficient, and it also supported by the observation. As you can see, here is the photospheric emission model. It is like combination of the black body and the band. Here is fitting. And here, these are the data that is obtained from the gamma ray burst satellites in different detectors. And so it's also supported to be very narrow. Here it is the model that simulated spectral here. And this one is the photospheric, and this one is the synchrotron, fast cooling and slow cooling. And here, as you can see, this model that they produce, they created with the simulation fit the data better than the others. So, however, it has drawbacks that there are some expectation that this photospheric emission should be like very narrow. So it should explain the narrow emission. However, blackbody is very sorry. I have to come back here. So the expectation that it is nearly thermal flux. It is like a blackbody, but it's the blackbody is too narrow. And the solution for that is that because the spectra that we see, it's not all of them fit with the blackbody, so it has to be a bit broader. So the solution is the geometrical broadening. Like it can be dissipation of the energy below the photosphere. So this is one of the things. Another one is the non-thermal part. If the non-thermal part is produced below or above the photosphere, and this is also not clear in that model. So also in the some of the studies, that it is shown that these two emission models can be seen together in one gamma ray burst light curve. Like here, Ajunar and Ryder took the large number of gamma ray bursts and they made a classification, and they see that like 1/3. So they made the classification, 1/3 of all the bursts are bright, long, single peaks with the large epic value, and 2/3 of all the bursts are multi-peak, and and they also find a cluster of short GRBs. So in this sample, they find that some source fitted with synchrotron model, and also some model fitted with the photospheric emission model. And in the other work, they find that, for example, they study the isolated 3 pulses, as I showed here. Like these are people call pulses, like 1, 2, 3. So they studied 3 pulses, and they find that first 2 pulse is the thermal, and the last one is the non-thermal radiation coming from the non-thermal radiation. So there is a way to distinguish these models. So the first is to study the spectral shape of the photon flux. This can be correlation analysis, and all measurements of the polarization, because from the thermal emission, people expect that the lower polarization, and from non-thermal emission, higher polarization is expected. Or the study of the minimum variability time scales, because from thermal emission show shorter minimum variability time scales, and non-thermal emission show long minimum variability time scales. And another way of distinguishing these models can be the multi-wavelength observations, like gamma ray, in gamma ray, X-ray, optical, and radio data. You can combine and check the model. So in my study, I work on the source that are obtained by the gamma ray burst space telescope. It is launched in 2008, and it has 2 detectors. One is large area telescope, which has a smaller field of view, and the gamma ray burst monitor has a larger field of view. And the LUT observed the high energy part of the, here you can see high energy part of the spectrum, and GBM observed the lower part of this spectrum. So, and it is consists of several detectors. And yeah, here, 12 sodium iodide detector and 2 bismuth German oxide detectors. And they have a different range of energy, as you can see here, purple and the green.
Husne?
Yeah.
The other 2 detectors, I see it as a pink and green colors in my screen at least. Why do we need them if the GBM and the LAT are covering the whole range?
So the GBM consists of these 2 detectors. So it's just under the, how the GBM detectors separated this color representing for that.
Okay.
GBM, the red is not separated than this green and the purple.
Okay.
Purple, yeah. So this is, you also saw this spectrum, photon spectrum.
Just a word to people who might not be used to high energy telescopes. So we usually think of telescopes as some mirrors or lenses for optical light. And as you can understand, gamma rays, which is what we're looking at here, you can see the photon energy goes into as high up as almost a tera electron volt. They're much more energetic, so they don't exactly use mirrors. They interact directly with all these chemical semiconductors and compounds, and to detect individual photons. Highly energetic, but typically might be a low number of photons.
Exactly, yeah. That's true. So in the following of the talk, there is 2 purposes. The one is as I said, the spectral evaluation during the individual emission to separate the emission mechanisms, because it is powerful to investigate the understanding of the physical process in the jets. And the second one is to understand better the physical origin of the short duration gamma ray burst, because it is one of the favorite source for the gravitational detection, such as, as you know, GR-170817. You will get more familiar in the following term. So our motivation is come from several papers that done earlier, and 4 of them is here. And I will go through with each of them what is done in them. So in the first paper, we select the 38 single pulsed burst with the T90 larger than 2 seconds, which is the long GRBs detected by the Fermi GBM. So this has to be bright enough that we can perform the analysis. And then we use the Bayesian block method to bin the data. The binning, the light curve is how we choose the bin is to we define the intensity change in the light curve. And where the intensity change is small, then we made the cut of the bin. The Bayesian block method do that process, cut the bin, and then it go to the other bin. So this is the differences between the binning in the Bayesian block and the binning in the normal signal to noise ratio. So then we made the time resolved spectroscopy onto each time bin, because in the time resolved analysis, each bin can display different behaviors. So we used the empirical model, which is called cutoff power law. And we also compare it with the band, and we find that the cutoff power law model explains the spectra better. And then we interpreted our results, and we interpreted the parameters that's obtained from this model. So at the end, we use the Bayesian method to analyze the spectra, because here the parameters are treated as random variables, and they can be described as a probability distribution the difference between the frequency method is that there the parameters are fixed. Here they are obtained from the probability distributions. So we here, as you can see, this is the part that I am speaking. Here is the light curve, and we made the bin of each of them, and we obtained the low energy spectral index from each of them, and then we made the distribution of that. However, we wanted to study that just the one has the maximum of this light curve, maximum alpha of this light curve. And then we wanted to study that part because we assume that single emission is responsible for the full duration of the pulse. So if this emission is explained well, then the others can follow. So this was our part. So we select the hardest alpha value, and then we put from each of the source 38 pulses, and we make their distribution, and we can see that 67 of them is the outlier of this line of the dot. So they are violating the synchrotron limit. And this fraction also found that it's larger than what is found before. It was 20%, and our case is 67%. So we also made a parameter distribution from the spectra fits, and one of them was the correlation between the intensity and the low energy spectral index. And this show very homogeneous behavior, like the 34 over 38 pulses has the positive and the linear semilog linear correlation in the semilog plots. And to quantify this observed correlation, we use the Sparkman rank coefficients, and we find that like 28 pulses have error coefficients larger than 0.7, and even 8 of them had a very strong correlation, like 0.9, and just the 2 of them had very weak correlation. Here, maybe like here is the light curve, flux versus the alpha. This is the correlation. Maybe I just explain here. And the different colors are representing this different significance of the bins. Like these red ones has the significance larger than 20. So to interpret this result, we use only the significance larger than 20 that is significant enough. So in the paper of Ryder, because we wanted to interpret like as thermal, this is the distribution from the previous slide. Here, distribution of the low energy spectral index. Here, we know that this part explained with the thermal emission very well, and this part can explain with the synchrotron emission very well. So what is the emission mechanism between that two parts? So this was our main question. So we say that, okay, there is a thermal emission scenario, which is the broadening of the spectra, and it's explained following it's called qualitative photospheric emission scenario. This can be also non-dissipative photosphere. Around the peak of the light curve, the large entropy causes the photosphere to approach to the saturation radius, and so the spectrum is narrow. So the intensity, then we expect that a harder spectrum. And then when the entropy decrease, like here, this is this spherical model for this emission. Here is the jet, and here is it's saying this is saturation radius, this is photospheric radius. So when the entropy decreases, the photosphere is at large radius than the saturation radius here, in this case. And then the spectrum becomes broader, so then it became softer. So then we see such a correlation here. First, it is harder, and then it became softer. So then we said, okay, we can fit this correlation between the intensity and the alpha using this function. And this is the alpha of the slope of the fits. And sorry, this is the alpha parameter, and this is K is the slope, this is the normalization, and this is the intensity flux. So then the results was lying between 1 to 5, the key, this is the slope of the fit. So we also find for the cutoff power of the mean value is 2.8, and we compare this with the band. And then we go to the theory and we say, okay, what is the condition? Conditions that the flux variation is due to the adiabatic cooling in the constant phase from the photospheric emission scenario. And the alpha variation should be -1 to the 0. So we estimated the K value, which is around 3. So we compare this and we find that the 70% of the bursts are consistent with such a scenario that I explained earlier. So then the third motivation was that Ajunar made collect this large amount of short gamma ray bursts, and she made the T90. She made the comparison of the different parameters. 5 parameters she used, like T90, peak energy, low energy spectral index, high energy spectral index. And she find the clustering of the sources, and this is a T90 versus the low energy spectral index, and she find that the cluster 5 is the consist of the short GRBs, and they are mostly associated with the photospheric emission origin. So we know that the spectral properties of short GRBs are less studied than the long GRBs. So the evidence showed that the photospheric emission could play an important role in the short GRB properties. That's why maybe they are not observed often.
Husne?
Yes.
Can you explain again why cluster number 5 is the best for this scenario, and not at least maybe the number 3, the green one?
Yeah, maybe I am missing here to add another plot that she showed. So she made a clustering, and then she select, because she's finding the group. So then she select this group, and then she tested that, like here, like for example, in the photospheric emission model, what is the expectation? Should be like the harder spectra here. So then most of them are here is showing such a harder spectra. And also she made another test to explain why it is more suitable. And so she concluded that this class is mostly consistent with the photospheric emission origin.
Just to make sure, this plot, the vertical axis, it's time in seconds, right?
Yes.
Log time in seconds. So this is showing long GRBs as well, right? Somewhere between the line between 0 and 1.
Yes,
is
exactly.
2 second line. So I guess the blue, purple, red, and even most of the green are actually long GRBs.
Yeah, they are like a combination of the long and short GRBs. And I think there also, not I think, but there is also the short GRBs in the other classes. But here in 5 is mostly the short GRBs.
Yes.
And then that's why it is like, here is the long GRBs indeed.
Yes.
Yeah, for
But
example.
do you have some, maybe I missed that and you said it, but is there a typical time that I can associate to long GRB?
Yes, exactly. It is the long GRBs is T90 larger than 2 seconds, which is, it's like, this is 10.
On the long scale, 2 seconds will be about halfway between 0 and 1, right?
Yes.
Yeah, exactly.
Formally, 3 point something, the square root of 10, will be halfway between 0 and 1.
Mm-hmm.
So you can imagine that basically green clusters 1 to 4 are probably in time they fit a long GRB better than a short GRB.
Yes. Yeah. So this time larger than 2 seconds for long GRBs and smaller than 2 seconds for short GRBs. That's why it's here.
Do you know
but there are some, yeah. So, yes.
Do you know what is the distinction between clusters 1, 2, 3, and 4?
So the way that it is like the one peak, because it is like some of them show. She also compared the variability that I explained earlier, like if it has one peak, 2 peaks, 3 peaks, multiple peaks, or this is the variability, the properties. So she separated them in a different way. That's why the definition change. I showed
it's a 2D
here
representation. It's a 2D representation of 3D space.
Exactly. Exactly. Yeah. Maybe if you are interested, I can just go to.
Also, cluster number 4 has really significantly less data points. I'm wondering why, and they are like in a almost single vertical line. They have almost no width.
So yeah, cluster 4 looks like physically it's very well defined and disjoint from the others.
Yeah, exactly.
So do you see my screen in different, or I have to share different screen? Do you see my presentation, isn't it?
Only the presentation.
Yeah. So
motivation 3 for GRB.
Yeah. So I don't know how to change it actually, but it is like so there is exactly 3D like with the all parameters, and then she also study. Yeah, I think it is mostly when I study her paper, it's mostly concentrated on the different pulses and different different categories in the like fluence, flux, peak energy, and so then it is a combination of that 5 parameters create such a class.
Okay, and just to make sure I remember this correctly, alpha is the spectral index.
Low energy spectral index, yes.
Negative,
and it's not alpha max here.
Hard.
No, it is not alpha max. It is alpha.
Okay. And
alpha,
which side is soft and which side is hard for alpha? High is hard or low? Or
so
soft?
If it is smaller than 0, like on the left side, it is throw to the -1. It is soft, and if it is larger to the 2, 1, 2, it is harder spectra.
Okay, thanks.
So another motivation was that in the paper of Ajiner, Raide, and you, they generated series of synthetic spectra expected from the photospheric in a non-dissipative GRB jets. And so these are the generated spectra. And this is a significance with larger than 20. And then they also made a significance larger than 300, that they can obtain the better, like a smooth like curve. smooth line. So then, and this spectra used the empirical model's cutoff power law model. So then they find that the distribution of the low energy index, here is the low energy index, is between the -4 and the -1. And it's peaking around the 1. So this was then compared with the distribution of the maximal time result, the maximal low energy spectral index obtained from the U, that our first paper. These are the alpha max that we obtained. So then she put here, and then she said that, okay, above this line, it is 1/4 long gamma ray burst is consistent with the non-dissipative outflow, releasing its thermal energy at the photosphere. So that this 1/4 of the long GRBs are consistent with the photospheric emission. And so in our analysis, we follow the same analysis method in the first paper, and we selected 68 single pulsed bursts with the T90 smaller than 2 seconds. This is the short GRB definition detected by the Fermi GBM. And we use, so we select each pulse time bin that has a maximum alpha value, a low energy spectral index, as it is done in the first paper. And we use the same curve that is obtained in the Ajunar paper here from the synthetic spectra. And we test the same methods. And we said, okay, we find that the 1/3 of short GRBs are consistent with the non-dissipative photospheric emission. And here is the alpha max and the peak energy. This is the plot. And here is all the short GRBs. And there were some outliers. We just show them because they had, for example, this green point had the 2 pulses. So, but most of them was consistent with the photospheric emission. These 2 had the 2 pulses, these 2 sources. One was consistent with photospheric emission. The other one was consistent with the synchrotron emission. So this was very bright source, and this was very faint source. We just wanted to outline them with different. Yeah.
Why did you check alpha max when I'm comparing to the previous one is only alpha?
So this one is also alpha max. She didn't write, but it's also alpha max.
Okay.
So for alpha max, we assume that only the one emission mechanism produced such a gamma ray burst. And so if one is suitable, which is the hardest value, then the following should be explained with the same emission mechanism. If the first one is failing, that doesn't fit the hard part of the spectra, I mean then this can explain with the synchrotron. Like it's easy to distinguish if you use the alpha max, but if you use the alpha, then it's difficult to separate it for burst by burst based, let's say. So then we computed the Lorentz factor in the constant ways, and when we made such a computation, we get very interesting results for the source above this NDP line, the non-dissipative photospheric emission line. So why we computed the photospheric, casting Lorentz factor in the casting phase? Because this is the distribution of the alpha. It is alpha for all GRBs. That is from the Ajunar paper that she used 1,115 GRBs. And then here is the expected alpha distribution from the casting phase, from the non-dissipative photospheric scenario, and this is the expected distribution of the acceleration non-dissipative acceleration phase from the non-dissipative photospheric emission. Since our data is lying between minus like 5 and something like here, almost 0, so we decided to compute for the casting phase, Lorentz factor from the casting phase. So we saw that when we compute this Lorentz factor and put it in the distribution, this is the Lorentz factor n, eta, sorry, not the n. And so we see that this black bars represent the short GRBs, and they have a B model distribution. This is the KD distribution. Here we also compare this with the long GRBs from the first paper. And as you can see, it is just seen in the short GRBs. And we also wanted to check, since we saw this, we wanted to check the hardness ratio, if there is a distinction between two peaks. As you can see here, the green, the black ones is the peak one, which is suitable with the long GRBs, and it has a softer alpha value and a smaller Lorentz factor. And the green ones are the peak 2, which is each has a higher alpha value and the larger Lorentz factor. And we also wanted to compare like above the NDP line for short GRBs, below the NDP line for short GRBs, like above is black and below is the red. And then for the long GRBs is the same for blue and purple. And as you can see here, it's like some kind of correlation between the hardness ratio and T90, that this part, which is the here, exactly here, it is the peak one, more suitable with the long GRBs. It's more softer. But here, the hard ones are very outliers. So, and then we also checked this correlation between the T90 and EPIC. We find that there is a correlation, like between T90 and EPIC. It's with the index of minus 0.5. When we consider the whole sample that we used, this correlation disappears. So we conclude that so this short GRB population composed of two separate populations. The one is the continuous of long GRB, as I was mentioning here. And the second one, also here you can see, because it's more suitable. The second one is the more distinguished with the different physical properties, like more suitable to the short GRB, really the short GRB definition. So our conclusion and discussion come after this result. So we find that 1/3 of the short GRB being consistent with having poor thermal origin. So the thermal emission is very common among the short GRBs compared to the long GRBs. And another fraction that is seen here can be also explained with the photospheric emission. However, it is like with the sub-photospheric energy dissipation model. But this emission is often accompanied by the additional emission mechanism like synchrotron, and which makes the definition of the photospheric emission difficult. So finding a correlation between T90 and we also these two emissions see those two emissions in the same gamma ray burst light curve can be explained also when we make a cut at the peak energy, which is here. For example, here we made a cut 800 keV, like around here, and we just consider this part and made the correlation between the peak energy and the alpha, and we find that there is a correlation. So this also show that there can be two emission mechanisms. That's why we cannot distinguish. So, and the third point was that we've at early times, the thermal competence is mostly dominant. At longer times, it is since it is accompanied by the second emission mechanism, then it became subdominant instead of dominant. So the last discussion was concentrated on this correlation between the T90 and EPIC. Higher peak energy corresponds to the shorter burst duration, we figured out. So the corresponding correlation is found in the flux. We made also the correlation between the flux. We didn't find any correlation. And this implies that the similar amount of energy is released in shorter time. And this leads very high temperature. So then this can be explained, this can be give a clue for the understanding of the progenitor models, and also the explosion mechanism in the short jet is mostly like considered as a thermal. So this is the end of my talk. So
thank you.
Thank you. Hope it was clear.
Yes, but I have a question. Like
yes.
A most basic question.
Yes.
And how can I, let's say, as a physicist that is dealing with gravitational waves, how can I help with this research?
So so this is
I mean,
on the
it's I can, and Ofer, correct me if I'm wrong, because I can say that this is an electromagnetic counterpart for our like regular signals. But are there any, like, in real time, can I, let's say, put my satellites or my telescopes to the right direction when I'm observing a gamma ray burst, or is it even practically possible?
So I mean, this is, as you remember, I mean, in this work, I don't know how it can, but this is the short GR-BIS. So it's like, if we explain the short GR-BIS better, then when we make such a observation with the gravitational wave, then we can, this is like mostly try to understand what is the origin of short GR-BIS. Because if it is like thermal emission, non-thermal emission, so where it's coming from, this emission. So in this work, I cannot say if it can. But for example, the next project that I am doing on the explaining the Pluto emission, our concern is more concentrated on the weaving angle. So as you know, this 1708-17 is observed like in the larger weaving angle. So that's why maybe it is low energy. So people are making some comments. So maybe that can if I can figure it out, if it is really the weaving angle, maybe that will explain that GR-BIS. But yeah, it is just mostly like here we are trying to understand the origin. If we understand the origin here, then if we find a constant observation, then we can start speaking about what it is.
Okay. Ofer, can you add something? Like
yes, this is maybe.
Yeah. First of all, for some context, GR-BIS are complicated and we don't understand them. as you can understand, even from the, if you read in between the lines of Husne's presentation, what you might see is that we're trying still to classify different types of GRBs. So there's the classification of short and long based on how fast the energy is emitted, and we see that that's sometimes related to the shape of the spectrum, hardness or softness of the spectrum. There's this clustering based on number of pulses and other effects. We try to find correlations and see if they match, if they explain part of the populations of GRBs and maybe some better than the others. We're just trying to classify them to understand what are the constitutive and descriptive relations describing what these GRBs behave like. We still don't know very well what is the actual driving mechanism behind GRBs. So for the short ones, there's strong evidence that it comes from a binary neutron star merger or a merger of one neutron star and one black hole. For long GRBs, there's the collapsor model, but a collapse of something to a black hole or neutron star. But that's still only very general. We don't really know the math. We don't exactly know how it happens. We don't know the equations of state involved. We don't know the evolution involved. And then, of course, the expansion of the jet, which you saw was the inner shocks and external shocks and all this thermal stuff, synchrotron radiation, all these things that are happening all together make it hard to really study with any definiteness. What gravitational waves do is they offer us a new window on the same events. So, for example, the great success of GW-170817 was that we saw a binary neutron star merging in gravitational waves in the same location and time as what looks like a short GRB. As Husne said, a very non-typical short GRB.
Even it is not a typical one. It has distinguished classification.
Yeah, it might be either a new type of GRB, or it might be a short GRB viewed off angle from sideways. That question, by the way, will definitely be answered with gravitational waves, because when we have more detectors and we can better study the orientation of the source system, we can know what the viewing angle is. But
here it comes to the question in my mind that then what we observe with the gravitational wave will be always in the viewing angle, which is larger than the what is expected. This is another question, that the gravitational wave source will have a larger opening angle on the jets.
We are definitely more sensitive angle-wise to gravitational waves than to GRBs. GRB jets are collimated to very, very narrow jets, and gravitational waves are almost spherically emitted. You don't see anything on the plane of the merger, but starting from a very small angle off of the plane, you can see the gravitational waves. So if Husne goes back to the angular openings of the BATSI versus LAT, or GBM versus LAT detectors, you can imagine that we're a lot more sensitive to gravitational waves. We can see them from everywhere, basically. So we can answer questions about the mechanisms happening leading to short GRBs, maybe even to what's happening within the expanding jet. And when we finally associate some gravitational wave with a long GRB, then we can really start probing the driving mechanism, what's called the engine of the GRB. If we can analyze whatever is happening inside gravitationally, and it probably will not be just a merger event, so it won't be the regular CBC chirp that we're used to. We might find a whole mess of a spectrum of gravitational wave excess power coming during or just before a long GRB. So that's kind of a burst for us, similar to what we might see from a supernova or other events, and just a whole new way of looking at these events. And as you can see, any piece of information we can scrap about these events is helpful because we really don't know what's going on.
Yeah, I think the more observation with the gravitational wave and the electromagnetic counterflow of gamma ray burst will show us if what is the process under this. It's like a large viewing angle or different class of gamma ray burst, or it is same, or it was just like coincidence, or yeah, this will distinguish. It's just now it's based on one observation, but more will bring something.
So just to make it clear, so in present times, it's not so possible because we are able to detect only black hole mergers, at least 99% of them.
That's not true. We have detected at least one binary neutron star merger, perhaps two.
Yeah, but there are so few events that are not black hole events. We need to, let's say it's only a future world collaboration that will be possible because we don't have like a significant amount of data about on neutron stars collisions and mergers.
We have short GRBs all the time. We didn't detect the gravitational waves passing the threshold coming from or correlate with those events, but that is a search one can definitely do. Look at other short GRBs that we find and try to find the distance and try to see if any of them are close enough to have a gravitational wave signature. Or compare the list of long GRBs and look for things happening at the same time in the gravitational wave data, which we now have accumulated for about a year of operation in 03, and actually a year and a half if you include 02 and 01 as well. So
yeah, there are several work done on that direction, like searching deep in the archive, and if there is similar events to do this 1907, 1708, 17, and like from different satellites. And also that there is large collaboration for the electromagnetic counterpart of this, such events on the ground-based telescopes. So yeah, these are like people are waiting. If there is something happening, then they will search. But these are the good topic to go deep or have some idea and work on it. It's a future project, I can say.
I think one of the Astro seminars we're going to have this semester is by Marco Drago from Italy, who was the first person to see a gravitational wave. He was the one who caught GW-150914 in 2015. And he's a burst person. He looks at bursts. So not necessarily modeled, well-modeled template searches like the chirps that we look at, but basically comparing irregularity patches of time and of the sky that correspond between the two detectors, or now 3 detectors and soon to be 4 detectors in 04. And if you can match any of those to a GRB, long, short, or any other class, then that's also a way to kind of bring these two fields together in multi-messenger astronomy.
Yeah, and also compare properties.
And even if you don't see something, you can have negative results, and upper bounds are also useful. If you can say that some astrophysical event which you saw with Fermi, it emitted radiation, was not accompanied by any significant gravitational wave activity, that is also restricting the models which one can propose for what caused this GRB.
Exactly, yeah.
Okay. Any more questions? Okay. If not, we'll thank Husne again.
Thank you. And I maybe should stop sharing.
Thank you very much.
Thank you.
Remind everyone that Husne is a semi-permanent or long-term member of the department, working with us. So if any of you ever have any questions for her, you can
yes, for sure.
knock on her door email. We can invite her to more meetings. If any of you are interested in GRBs, you can work with her or with me. My first paper was actually on gravitational waves from GRBs in 2013. So GRBs are definitely an interesting candidate source. So far confirmed once, but we're looking for more, and it's a free topic to work on.
Yeah, when you think about the future detectors on the gravitational waves, it's like the future might be very bright. And that's why there are really huge collaboration preparing themselves for counterpart observation of the gravitational wave sources. Yeah.
Yep.
So my next project also, it's more linked with this weaving angle, and there are work to do, but I need to see with Asaper how he want to do and how things. But if someone interested, we can try to match. And yeah, some projects for the master students. I also want to say that our meeting with Asaper will match with this meeting, but it will start at 11 o'clock. So I might attend just 1 hour of this meeting. So it might be like more interested with the binary black hole, or these projects might be earlier than the waveforms projects. So that's I wanted to suggest if it is suitable for you.
Sure.
Yeah. So then I let's see.
Okay. So we'll let you return to Asaf's meeting now.
It will be next week, starting from next week.
Okay. Okay. Thank you.
So I am still here.
Yeah, you're welcome to stay.
Thank you.
I will stop the recording now. If I find how to do that.